Good afternoon, all. Welcome to the class, very important class today for talking of the new data structure, which is going to be called as a linked list. And the pointers and knowledge will be extremely desirable. So I hope you remember the 6 rules R1 to R6 of a pointers. And those pointers rules will be definitely advisable to be referred. Yes, primarily array-based roles will not be much used. So R1 to R3 will be more used and R1 and R2 will be much more relevant. So remember these rules. And now we are going to see that what is a linked list. Of course, it's another data structure, and another data structure will mean that we are going to use it for various different kind of utilization and operations. Another important data structure. But primarily linked list effectively means another storage. When I say another storage, I mean earlier you have used array as a storage, and versus other option could be linked list as a storage. Operations on the linked list can be as the way we have been doing over arrays, like any insertion, deletion, sorting, searching, etc., whatever. Polynomial, sparse, linked to a stack, queue, anything via array we have done. Same thing can be done via linked list. So we can have a stack using array also. We can have a stack using linked list also. We can have a queue, we can have a polynomial using array also, using linked list also. Obviously, question comes when to use array, when to use linked list, because both are storage and operations can be anyone. So effectively, what is the advantages or issues with the arrays? Then arrays have mainly one biggest advantage, that individual element access is very fast. I want to access any element, let's say I, is extremely fast in unit time. Why unit time? That once I know that I want to refer to, let's say 90th element, I will simply say array 89. Or if I say index 90th I want to refer, I can simply write array 90. And this is directly accessible without going through the previous elements. Why? Because this is internally equivalently converted to star of ARR plus 90. And this address is guaranteedly correct. And this is the address of element of index 90. That is effectively 91st element. And because I know directly the address, which is directly computable, I can directly access this element. Some situations could be there where we are supposed to go to the element after going through the previous elements, then only I reach to the correct address. So then it will become slow, but in arrays it is definitely useful. But the arrays has some disadvantages also. First disadvantage, it always requires contiguous memory. If you have an array required of very big size, you require that a big memory. For example, if I wanted an array of 5000 into 5000, a 2D matrix, that will effectively mean I need 25 into 10 raised to 6 integer memory as contiguous. Contiguous memory might not be available in the RAM or in my computer internally. It might happen that, let's say I have got some free memory here, which is, let's say 200 KB. Then somewhere else I have got, let's say 700 KB. Somewhere else I have got, say 1200 KB. Somewhere here I have got, let's say 800 KB. Totally, maybe you can see I have got more than 3000 or around 3000 KB available. Somewhere here I can have 500 KB. So I might have individually not available as a 3000 KB. I need a 3000 KB memory for, let's say, some array, but contiguous memory is not available, although separately that much memory is available. So array cannot be stored in such situation if array needed 3000 KB. So I have 800 plus 2000, 200, 1000, 1700, 2900, 3400 available, but not consecutive contiguous 3000. So that's one disadvantage. Not only this, then array has additional disadvantage that your insertion and deletion operation, they are not in unit time. In general, if you want to do any insertion at any random location in the array, it is not in unit time. For example, if you have an array, you have these data field up to this is, let's say, n, and you want insertion here. Say insert value here. This will mean all this data needs to be shifted. Shifting needed effectively means a loop needed, and loop needed effectively means not unit time, some extra time complexity. So unit time means no loop needed, simply 2, 3, 4, 5 statements, and you are able to do that. So insertion becomes very costly in case of arrays, and similarly for the deletion also. In the deletion also the same problem. If you have array field like this, and let's say you wanted to delete this element, but if it has got data filled up to this location, up to this was your n or n minus 1, this is your nth element, then you have to shift all this data towards left by this place. Only then you are able to actually delete this element. So deletion also has the same problem. For all such situations, then there is an alternate storage which is called as linked list. So alternate storage of linked list means that in general, we store the data through linking. What does that mean? That if I want to store, let's say, values 15, 3, 11, 5, 7, and so, then I will say this will be stored as a linked list whose initial address will be known to me, like array initial name or etc. But they will be stored via linking in a way that each element has a current data and stores the address of the next element. So no consecutive memory needed. I have all individually elements stored, and each element will store the address of the next element. So if I want to reach to 7, if I want to access, say, 1, 2, 3, 4, fifth element, say fifth element, that is 7. Then 7 cannot be accessed immediately. I can't write like start 6 or start 7. That I can't write because no contiguous memory is there. I have to reach to first 15. From 15, I will come to know where next address is or where next element is stored. So this element could have been stored at, let's say, 800H. This element could have been at 1200H. This element could have been at 300H. This element could have been as 2000H. This element could have been at 400H. It could be anywhere randomly, and I will reach to first element, then second element, then third element, then fourth element, and then only I will be able to go to fifth element, that is 7. So in the linked list, access is a sequential. Hence, if I have the individual access to be done, then individual ith element access will require a loop. And unit time is not possible. So in array, this individual access was unit time, but now it's no more unit time. So that's one point which we have to remember always. Having said that, I say, but there are some advantages also. In case of linked list, no contiguous memory needed. One element only. So if I want a list of, let's say, 10,000 elements or 1 lakh elements, I don't need 1 lakh contiguous memory. I can store one element, some at another address, another element, and so, and it could be 1 lakh elements at different addresses. So all that can be another way of doing the same thing. And if I want to just follow this, then this is one of the good advantages of the linked list. Secondly, insertion and deletion can be in unit time. Why and how we will understand later, but without loop at particular position, insertion and deletion will be possible. So this becomes advantage of linked list. So depending on situation, you will choose which of this storage to be used. Say if you have a array to be stored or linked list, you maybe first of all you can decide how much contiguous memory needed. If contiguous memory of that big size is available, both choices are okay. Not available, straight away means array cannot be used. The only choice is linked list. Available. Available will mean you can use array and you can also use linked list. You have both choices. So if not available, guaranteedly array is ruled out. If available, array versus linked list. So the choice will be based on how much is individual access and how much time you will do in the access of insertion and deletion. So how many times you need individual access of elements? Somewhere in the last or not in the starting. Because in the starting of the linked list, faster insertion access will be possible. But if you require some random element access very frequently, then obviously array is useful versus how much insertion and deletion you will need. If you need insertion deletion more frequently, then you should prefer linked list. If you have this to be very less times and individual element access is more, element access, I will say individual element access is more, then obviously that will mean if less insertion and deletion, individual access more, it will mean array is a good choice. So accordingly, you will decide. But if, of course, memory must be available, and if memory constraints come, then there is no choice. Well, having said that, I know now linked list has its own utilization. So a lot of applications do exist, obviously, and we will be studying in them in a lot of details. So basic concepts of linked list will mean that now my individual elements, if I want to create an array of n values, so n maybe let's say 10 or 1000. So you will store first value as a first node, which will be pointed by a pointer known as start or something similar. Then it will have the address of the next value, which could be 20. Then it will have address of next value where 13 is stored and next address is stored. It stores 18, next address stored, etc., etc. And let's say once you have the last node, normally we will say this node will have finally the address to become null. So last node will normally be terminated by null pointer. So I say linked list by default will mean starts with a special pointer, which could be named as a head or start. In some books, you will see start word used. Some book will say head pointer used and terminated by null pointer. So it's a linked list, linked with each nodes, terminated with null pointer, null address or null pointer. So having said that, now let's see how do we implement. So each of this node, each of this box which we have used is called a node. So your main connection or primary component of your linked list is always a node. What node contains always two things. it contains the data and the address of the next node. So normally we say the node has two components, data. For example, data we mainly use, or we will mainly focus, I will say we will rather in future, we will mainly use int or char mostly. But in real life, data will mean full structure. For example, it will mean students' record. So it will have all fields like roll number, name, father name, address, mobile number, etc., etc., fee paid, etc., etc. Lot of fields. All fields will be collectively treated as a data. Similarly, it could be an employee record, it could be a book record, it could be a bank record. So a lot of data will be there, which I need to store in my list. Along with the data, this will be an address to the next node. So my each node will always have one or many fields for the data plus one extra field for the next. How to create this? This I create via type def. Type def struct, because it's a structure ultimately. Node word, not a reserved word, but normally we use conventionally word node for such things. So you can use node or any other word. It will have for the time being data. As I said, we are mostly using integer. But in real life, it could be like int roll number, comma, char, name 30, comma, char, father name 30, comma, address 50, fee as a float, etc., etc. All fields plus address of next node. Address of next node means a pointer. So obviously it is going to be a pointer. Next is a pointer. To whom? To another node. What is a node variable? So I will say now it will actually write again struct node. Struct node we were starting to define and declare. Same struct node is reused here. So this is called as a self-referential structure. So structures who use the same declaration word for its one of the fields, they are called as self-referential structures. And self-referential structures like linked list node are very common. Then I will write here word node and a semicolon. Note that semicolon is a must here. By this, what I have declared is that node is one structure. So node is a structure. What it contains one field as a data, which is currently integer, other field as a next, which currently is a pointer to node type structure. So it is supposed to point there. While using the word type, the advantage becomes node has become a standard data structure or standard data type for future usage. It is as good as integer or float or char or whatever. So the way you use int, char, float data type, now you can use node also as a data type. Advantage, now you can declare node-based variables. Any variable of node type can be declared by using word node directly. What I need now? I need start as a pointer. Pointer to whom? To nodes. So what I need? I will make a global variable start as a pointer. Start is a pointer to node type. For the time being, I am taking global. Later, we will convert that also. So node is a global variable. And similarly, I can have some more global variables if needed. For the time being, I don't need, so I'll just proceed further. So let's say node is now declared as star start as a global variable. And now maybe I start in my main some of my programming. So by doing this, what I have created is one box which is named as a start variable, which can store some address. Remember, this box is not node, this is only address. It doesn't have data field. Start is a pointer. So it's a pointer field. Means it will have something like, let's say 2000H, something like this, but no data, nothing else. So it's not a full node. It is a pointer to some memory which has to be a node. That's it. So I have initially created a start. Let's assume I want to create a linked list. For the time being, I assume I want to create a linked list of this type. To be precise, I will say I will write here null, whether I show it like this or I store it like this. I want a list like this to be created. For the time being, I am making it a very simple list that it has only 2 nodes, and I want to generate this list with fixed values 5 and 20. Later, we will refine for n nodes with general values. First of all, let's go one by one. I want to start to point to this node and have value 5 and some linking. This node currently doesn't exist. How to create? So because we are using linked list, because we are saying contiguous memory will not be needed for a lot of data, so we will say one data will be stored at a time, one element will be stored at a time, and that also will use dynamic memory. So via linked list, we always try to have dynamic memory. Whenever we need, immediately create. Whenever you don't need, you can free that memory also. Ideally, in dynamic memory discussions, we might not have discussed the free statement last time, but yes, that is an ideal situation. So I'll just say that whatever yesterday we have discussed, say if you have done malloc for say PTR equal to some data type and type casting, etc. Then you found, let's say, average using PTR, etc., etc. Once work is over, free PTR statement can be written and it will free the memory allotted to PTR variable. Whatever size memory was allotted to PTR, same will be freed. So if a PTR was allocated, let's say 4000 bytes to PTR through malloc, so here you have given 4000 bytes. PTR got this memory. As soon as you write free, these 4000 bytes are free now. So later you can have another variable PTR2 to have another 2000 bytes, and you will be easily getting that you don't need extra memory. So in case of array, memory doesn't get free. Static memory doesn't get free. Static or compile time memory, that will get freed only once the function is over. Only after its scope is over. And scope over effectively mean if it was variable inside the function, when the function will be over, only then. If it was inside the main will end only once the program ends. So effectively the memory will remain allocated to that variable main till last, till the program ends. Because main will execute, although main is a function, but till program doesn't end, if main has one array of, let's say 4000 bytes or 2000 bytes, this memory will remain reserved, cannot be freed. But if you did dynamic memory, you can free anytime. Dynamically allocated memory can be freed anytime and can be reused after that by anyone else. So ideally, A good practice is whatever dynamic memory you give, programmer must have a habit that whatever memory you allocate, free always. Whenever its work is over, whatever memory you allocated, that must be freed by you itself, allocated by you. If you don't know when to free, maybe towards end of that function you must free. If you know it can be freed before, you should do that. So I want to generate this list now, coming back. So I have to have dynamic memory usage for the linked list, and it will be possible to be freed also at any stage. First of all, I need this node to be created. So how to create? I will say this node must exist, and dynamic memory will be the easiest way to do. So first statement which I will require will be start equal to some typecasting to be done and malloc. Malloc how much? I need one node only. So I will say one or nothing to be written, but the size of will be must. Size of a node. Now, if you have declared type def, you can use the word node. If you have not declared type def, then you will be forced to write every time word struct node everywhere if type def is not used. So in some books or in somewhere else, if you see struct node written, don't get confused. If you have not declared your node through type def, then every time you will write node, struct node, otherwise simply word node will work. Similarly, here also, whether you want to write struct node or node is your choice. So accordingly, you can use a type def or not. So this size of node will tell, let's say I need 20 bytes, 40 bytes, whatever node requires. One node only. So one into this, or by default it is one. So n I am not writing, one node at a time created. Here, typecasting. This is a memory of a void type. It is to be considered as pointer. Definitely of what type? Of node type. This is a memory. So by this statement, malloc, you got a memory box created. And start is pointing to this address. So my start earlier was garbage, now start points to this address. This typecasting treated it as effectively a kind of a node which has a data field, which has a next field. So this kind of a logical boundary gets identified as soon as you say that this is a node pointer. So node pointer mean let's say for data I'm using 12 bytes and next 8 bytes are for the next. So those boundaries get defined because node knows how much memory was there. Earlier it was 20 bytes. Now it knows 12 bytes for the data and 8 bytes for the next, etc. This work done. I want 5 to be stored where? Into data field. So what I will write? I have to assign the data field. How to write? Effectively, I have to access this field. How to access this field? When you use pointers, the syntax says start arrow data. Arrow is meaning a dash followed by a greater than symbol. So we call it arrow, but it is 2 symbols and single operator. So it's a one operator, although 2 symbols used, like plus plus, 2 symbols, but one operator. Start arrow data is the way to access this. Ideally speaking, we could have used based on star also. I say, what is a star start? Rule R2. Start is an address. Star start means a value of address. Value at that address means it's a full node. Star start means it's a node type pointer. So star start means a full node. So star start becomes a full node. I want this full node means full structures dot field data. So with the structures earlier you was using dot field and dot was used to refer to individual field. Same syntax can also be used. This syntax is also correct, but primarily or conventionally with pointer based not with the star used, arrow is used. So arrow is equivalent to not using star and dot directly, that is accessible. So these are equivalent. This and star start means value, node value full. Out of that node value, dot based field access, and similarly dot next. But directly you can use start arrow data. So I can write start arrow data equal to 5. This means now start is pointing here. This field has got 5, and this is some garbage data, some garbage address. So this statement has done this. Now I can assign here null if I want. So if I write start arrow data equal to null, will mean null gets stored here. Null means the address is null. It doesn't point anywhere. So null is a reserve word, capital N-U-L-L, in caps only. So it's a reserved word, reserved symbol, and you can always use to terminate your list. By this process, list ends. But I'm not willing to end the list. So maybe, oh, sorry, this was start arrow next. Sorry, this was wrongly written. Next is a field name, which I wanted to change. But of course, I don't need. I need the list to be created as 5 and then followed by 20. So if I say I have currently, so I will just now take a new page and explain there with all the in a more clear words. So what I have understood now is currently I have start equal to malloc, and then I said start arrow data equal to 5. So I want a list to be created as something like this. Till now, what I have got is created start pointing to this node, have 5. Now, effectively what I need is this linking to be done, new node to be created, within that node 20 and null, etc. to be stored. How to get a new node? Anytime I want a new node, I will say, I will take malloc. So now what I say, let's use another variable, say named as a temp1, and temp1 also to be done malloc. So I will say, now I will take temp1 and I will also do it malloc to get the proper syntax. And this temp1 main can have them as a local variable. No need to have it as a global because this is a temporary variable. List will have only start variable once list is ready. Rest everything is a temporary. So temp1 is a local variable created of a pointer type. By saying this malloc, I generated another box. Now this box is ready. This box is pointed by temp1. This box is pointed by start. You have to create the list like we have done above. Think of what is to be done. I say you need total 3 more steps to do what we have done. Can you think of those steps? Pause here, try to write those steps. And these steps are easy. We have already discussed something similar for each step, and you can write that. Pause here, try that, and I'm giving few seconds of pause, then I will give the solution. So assuming that you have tried and ready with your answer, let's do those steps one by one. What I need? Effectively, first of all, maybe I say I need to link like this. What I need? This is the next field, which is to be assigned something. How to refer to next field? Start arrow next is a field which is to be assigned. Arrow next or the dot, star, start, dot next, anything you say. To be assigned something. What to be assigned? Next is an address. Rule R1 will be applicable. Address can be assigned as an address because the next end variable is pointer type. So without a star used means it's an address always. It has to be given an address or a pointer. So it can be assigned another address. Which is address? Temp1 address. So this means that this pointer also points to the same node where temp1 is pointing. Effectively meaning, let's say if this address is 2600H, earlier in temp1 variable 2600 is stored. Here also 2600H gets stored. Effectively meaning, I'm pointing to this node. Done. One step down. Step 1. What next? I want here data to be stored as a 20. Step 2. How to do? This place, data field, via temp1 it can be accessed. Temp1 arrow data or star temp1 dot next equal to 20. Done. This work done. This field to be given null. So I say effectively I need temp1 arrow next to be assigned equal to null. So this list will become complete. But of course, I will not be willing just to do these works. These are pretty simple works. So I went very slow to create this. Just imagine I needed, let's say, a list of 4 or 5 nodes. So we should be able to loop that and improve that further. Let's say after this, I wanted 15 to be stored. So if I say now I wanted a list like this, how will you do? Finally, the list should have something like this. Could be further also. Let's see if I needed third node also, what you will do. Maybe you will say take another temp and proceed like this. Maybe I try to think, let's try to have this code repeated. So I say, let's have again temp1. So my start is this. Currently temp1 is this. And if I don't write this statement up to this work is ready, this doesn't exist. I want this. So what I want is another node to be added. Currently this much is ready. I say, let's have another node created. That is first step. So I will say temp1 equal to malloc. As soon as you wrote like this, remember, now you got a new memory and temp1 points here. But if a temp1 points here, now temp1 doesn't point here, not to 20. It points to the new node. Like earlier we have said, PA equal to %A. Later we said PA equal to PB. So PA, wherever earlier it was pointing, it is shifted to PB. Similarly, temp1 was earlier pointing here. You got a new malloc, you got a new memory, and temp1 points there. Maybe I'll say, fine, okay. Now I want this linking to be done. How to link? For linking, I need current node or this node's address and pointer. Earlier temp1 was available, but now temp1 has shifted. I can't link. So I got a problem. Maybe you will say keep temp1 here, make it temp2. Then I say I have another function, fourth node also, then temp3, then fifth node, temp4. How many temps I will declare? So I can't think of that. So I have to think of something generic. So what I say, I will say now, let's take another variable, current. So that every time I will keep current to the present node and next node will be always a temp1. So I will say current is taken as another node. That will mean I will also declare as another CURR of type this. So in that case, it will become a comma, and I have declared CURR also a temporary pointer, current pointer of node type. To current, no memory allocation needed. The current can point to any existing node. So temp1 is having the data. Current also points to this. So at present, I have start, which is always here. Start, I am not shifting because once the list is ready, start must remain here. So start is never to be shifted. I had here temp1 and 20 here. Now current also points to this node itself. Always current, this node always means starting address of this box. If this is having 40 bytes, this will mean, okay, starting address of 40 bytes. If this is 30 bytes, still means this. So pointer always means first address, starting address. That is always we know. Even if integer was there for 4 bytes, only the first byte's address, starting address. So now I say current equal to temp1. So current equal to temp1 is now this situation. After this, I can say that now I am going to again allocate the data. So again allocate the memory. So I will say now another temp1, same temp1 will be used and another node gets created, meaning that temp1 got changed to this. This box ready. This statement done, this box ready. Now what next? I say effectively these 4 steps will be repeatable, probably. So I say first step repeated, second step. Earlier I wrote start arrow next. If I write now start arrow next equal to temp1, it will be actually making something wrong. What will happen? Start arrow next will mean this address changes and this points to this. But I lost 20 in between. I wanted 5, 20, 15. But this connection will mean this node got lost and start directly points to next list. This node will not remain into the linked list. So this is incorrect. I am supposed to link current node to go to this. So I will say my statement, correct statement will be current arrow next equal to temp1. So once I did this, what happened? Start is here. Start will remain here, obviously. Start is linked to 20. Current pointer is this one. Temp1 is this one. And now I said current arrow next equal to temp1. Current arrow next equal to temp1. Step 3. This data to be assigned. So I can say temp1 arrow data to be equal to, let's say, 15. 15 got stored here. And maybe I will have another node later, again that linking to be done. I want to repeat. So what should be fourth step? Current should shift. Now current, this node's pointer is not needed because linked list is ready. And we go always sequentially in linked list. So my current will come here. And for that, I will write current equal to temp1. The advantage of shifting current is later temp1 is free now. Temp1 can be given new malloc and I can repeat. So effectively, I can loop this and repeat for any number of nodes to be created. Once loop will be over, at that point, I will say now list must be ended with null pointer. And from the above logic, I can see whatever will be the last node where I will stop, that will be pointed by current. So I could be always outside the loop write current arrow next equal to null outside of loop. So this I could easily think of repeating again and again. And effectively the same thing I could think to repeat for this data also. So what I will ideally say now, that what I want to do is simple, that my linked list creation will become, always I say, for the time being, I will assume that whenever I want to create a linked list, I will have creation done, that linked list creation will always have minimum one node, always. And I can ask the user. So for general programming, I will say data for each node should be read via scanf, etc. Secondly, how many nodes are there? That also should be not fixed as a 2 or 3. That also should be repeated. Maybe you can read n and accordingly loop made or whatever. Generally, what we do is we ask the user, do you want more nodes or not? So I will say create one node, 5 or whatever data he told, you have created. This is a start node. After that, I will say node ready. Ask the user, do you want more nodes in the linked list? Do you want to add more nodes? If he's, and you can ask him, press 1 or 0. So press 1 if you want to add that, or press 0 if you want to stop. So 0 to stop, 1 to add. One to add and 0 to stop. So give a user a choice. So your loop can be now accordingly made. Start equal to whatever malloc done. This has to be done. This rest coding, you think of what to do. Then you should be able to loop, and if user says 0, stop. Otherwise, create the list. Otherwise, add node. Once loop is over, finally, you will have arrow next, let's say current arrow next equal to null to end the list. So I will give you homework. Try to write a code, create a linked list, which reads the data from the user and asks user after first node will be guaranteedly created. It asks the user, do you want more nodes or not? Do you want to add more nodes or not? Press 1 or 0. And based on the choice, you always do that. This can be one practice for you for today's based logic. Then I say, second part is display the full linked list. Like array you traverse and display. So that display will effectively mean that if I have a list like this, say 5, 20, 15, 7, and so and so. So display process will mean that you always have your start pointer available. So from start onwards, you can go to any current node, print its data, follow the next pointer, print its data, follow the next pointer. So loop itself print the data and go to the next node. Go to next address. Keep on going as long as null doesn't come. So when you reach to the null, effectively your display or your traversal will be over. So I give you second practice problem, practice or try to display the created linked list. This all you can do in the main for the time being. Later we will do some structured and useful programming to display the created linked list. So you should try this also. And next class, we will discuss all this in more detail. So today's lecture is very important. You must practice today. Try to solve this and run this and see what really is happening. Make a clear picture of how logic is being developed, what is happening from each statement. From tomorrow onwards, some serious programming with the linked list will start. Today, what we have done is very simple novice programming for only beginners, linked list programming. But from tomorrow onwards, serious programming will start. So be ready and practice today. And maybe next class, you will learn something more than this. Bye-bye. All the best.